Hello, Mr. Simpson here with our third video for section chapter 14. This is section 3, relative strengths of acids and bases. Once again, you will see the learning objectives listed here for you. Please pause the video and copy those in your notes. Okay, let's talk a little bit about acid and base strength. I'm going to show you over here on the right-hand side, you can see a table with the 6 strong acids and the 6 strong bases. We need to get comfortable here with the notion of what that means, and I've mentioned it in prior videos, but I will mention it again here for us as we are starting this section on relative acid-base strength, is that the difference between a strong acid or a strong base, in this case let's focus on strong acid, is the amount of hydrogen that dissociates to form the H3O+. So if I had a strong acid, then this reaction would not be an equilibrium reaction, because 100% of the H plus that disassociates here, that as we've seen from the acid goes to the water, would transfer to give us the H3O plus. Okay, so when I have any acid that's not on this list, I'm in a situation of equilibrium where I have a percentage less than 100% that is being transferred to form that H3O plus. With regards to base, it's the acceptance of the H plus to form the OH minus hydroxide anion. So just again, we need to be really comfortable with that notion of the difference between a strong and weak species. Please make sure you copy these strong acids and bases down, and really all we can do is commit these to memory. There's no, you'll notice that there are some similarities based on like the halogens and things like that, but at the end of the day, we just need to memorize these strong acids and strong bases. Okay, so if the acid strength for a strong acid is pretty straightforward, because we get that entire dissociation. So whatever our concentration or the concentration of our strong acid equals the concentration of our H3O plus, and then once we have the concentration of H3O plus, we can get the pH. That's pretty straightforward. Same thing on the base side. So the majority of our work, the bulk of our work here in this unit, is going to be to determine the relative strengths of acids or bases that are on the weak side. And we do that using the acid ionization constant and the base ionization constant, Ka and Kb. As I take a look at these two reactions, and again, these are generic reactions for any acid and any base. You should also be it will make your life easier just to remember these two kind of generic reactions, because I can apply them to any weak acid they give me. I don't necessarily have to have the particular reaction for that weak acid. This can apply to anything. Now, if I happen to know what the weak acid's formula is, or they give it to me, I can actually go and do the real one. But these generic reactions for weak acid and weak base ionizations work just fine. Okay, so as I think about this, if I think about the first reaction, since it's an acid, we are going to be calculating the acid ionization constant, or Ka, and we should be at this point in time very comfortable with this process of setting up our K expressions. So products over reactants, coefficients become exponents, exclude solids and liquids. That's why you see the water does not show up in this expression. For our next reaction, we're dealing with a base. We see we produce OH minus. So we would be talking about a base ionization constant, and we would be, again, the process is the same, and this would be our expression here for this second for the base reaction shown here. As we think about acid and base reactions, we can think about what these Ka and Kb values tell us. So first of all, it's the relative strength of the weak acid. So the larger the Ka value, the stronger our acid. Larger the Ka value, stronger our acid. And then if we think about the relationship between our acid and our conjugate base, there's a relationship there as well. And then there's also a relationship to the Ka and Kb. So let's first talk about Ka and Kb are inversely related. So the larger the Ka of an acid, meaning the stronger the acid, the smaller the Kb of its conjugate base, meaning the weaker the base. All right, and then vice versa. And then you can see here that Ka times Kb equals Kw. So I'm going to write that again here. Because we have seen the Kw, we know the value of the Kw is 1.0 times 10 to the negative 14th. But for a particular system, if I have a Ka, I can solve to get its Kb, or vice versa, because Ka times Kb equals Kw. So that's a good reaction to make sure that we have in our notes. Okay, and so here you can see that relationship that I talked about a second ago, right? So as I get towards the side of strong acids, my Ka value is going to get larger. Okay, so over here on the left, we have larger Ka values because we have stronger acids. And then the effect that has is I have weaker Kb values, so weaker conjugate bases. All right. I want to talk for a second. This is going to be an important concept for us here. So because we are talking about something less than 100% of ionization, we need to be able to calculate a percent ionization in a problem. Okay, so basically this is how much, if I think about our generic reaction here. So what we would like to know is how much of this, what percentage of this H transfers to form our H3O plus. Okay, that's our percent ionization. How much acid? We know it's less than 100 because it's not a strong acid, but what percentage of that transfers? So really, it's a pretty simple setup, pretty simple formula here. It's the concentration of the H3O plus over the concentration of that weak acid times 100 to make it a percentage. Go ahead and pause the video here and copy this quick practice problem in your notes. So as we know from earlier sections in this chapter, since they give us the pH of 2.09, then I can calculate our H3O plus concentration, right? If I take the inverse log of a negative 2.09, I get an H3O plus concentration of 0.0081. Okay, so now I can calculate my percent ionization because I have my H3O plus concentration. And of course, I have the concentration of the weak acid that I started with. Okay, times it by 100 to make it a percent, and I get 6.5% as my percent ionization. You're going to want to make sure you're comfortable with this because this quick calculation, this quick percent ionization calculation can actually help us in some future problems here in this section avoid having to use the quadratic equation. Okay, let me say that again. Avoid having to use the quadratic equation from coming out of our last unit. I'm sure that is music to your ears. So I'll show you that in some practice problems here in a minute. All right, we're going to finish off this section by looking at some different acid-base equilibrium calculations. Acid-base equilibrium calculations. Okay, so here's our first type. So we're going to determine the Ka from equilibrium concentration. So they will give us all of our equilibrium concentrations right in the problem. What is the value? Again, the question here is, what is the value of Ka for acetic acid? So I know that, again, I can do, since they give me the formula of the acetic acid here, maybe I already knew that or could come up with the formula there, I can do the specific reaction here, but I could also have just used the generic reaction for an acid reaction. So either one works. It's not really that important, but I will go ahead and get my specific reaction here. Okay, and so they give me all of my concentrations. So my Ka is going to be the concentration of my H3O plus times the concentration of my acetate ion, anion here, divided by my concentration of my acetic acid. And again, they give us all those values in the problem. So I can just plug them all in and solve this out for my Ka value. Okay, so that's those are pretty simple, pretty straightforward. They give me all the concentrations. I just plug and chug and solve for my Ka. Okay, now let's determine the Ka or Kb. Again, I'm going to do a Ka problem here. Kb obviously would be very, very similar, just talking about a base reaction instead. From a given pH. Okay, so we got to think about what the pH tells us. And in this circumstance, we are going to be utilizing our favorite ice tables again. So once again, let's come up with the reaction. Again, since they went ahead and gave me the nitrous acid, I'll just go ahead and do my reaction with that nitrous acid. Okay, so we're determining the Ka again. Okay, so I know my expression here is, my expression for my Ka is going to be the concentration of H3O plus times the concentration of NO2 minus all over the concentration of my weak acid. Okay, but unlike the last problem, I don't really have that information yet. So let's think about what I do have, and this is where our ice table comes in. So I do have the concentration of our nitrous acid. So that's the 0.0516. And again, my initial concentrations of my products here would be 0 and 0. And as we know, liquid is doesn't matter here. Okay, and we can actually find, if I think about this, if I have a pH here, that will allow me to find our equilibrium concentration of the H3O plus. Okay, so if I do the inverse log of this 2.34, this pH of 2.34, I would get an H3O plus concentration of 0.00457. Okay, so again, that is our equilibrium concentration of our H3O plus. Okay, so now that fills in a lot of blanks for us. Okay, so because of our stoichiometric relationship here, our concentration of our anion is going to be the same. And now I know that my change here, because I started with 0, was this. And once again, since our stoichiometric relationships are the same, I know that that means my change here is to lose that amount. So once I've done that, I can come up with the equilibrium expression, or the equilibrium concentration of our acid as well. Okay, and now you'll see I have all of those equilibrium expressions I need to go ahead and solve for my Ka. And I get a Ka value here of 4.97 times 10 to the negative 4. Okay, how do you utilize an ice table there? Because while I had the initial of the acid I started with, the other piece of important piece of information I had was the pH of my solution. So that tells me the concentration of my H3O plus. Okay, and then I was able to work my way through to get my equilibrium concentrations and then solve for my Ka. Okay, one more here. This is calculating equilibrium concentrations in a weak acid solution, and basically, if I'm trying to calculate my equilibrium concentrations, I'm often also going to be asked then to solve for the pH. So, right, because if I'm solving for my equilibrium concentrations, that means I'm going to be solving for the H3O plus concentration. So along with that, I'm also often going to be asked to identify the pH. Okay, so pretty common question there. Okay, so this one has a little more to it, and this is where we can check our percent ionization, and if it's below a certain value, we can avoid using the quadratic. So let me show you what that looks like here in a second. All right, so as always, we'll do our reaction. This time I will just go ahead and use the generic acid reaction. Okay, and so now we think about what we have initially here. We know that we have an initial concentration of our formic acid, so of our weak acid. We know our initials over here are 0, but that's all the information we have. So there's nothing else about, there's no pH values here, there's no other concentration values here. So as I think about the work we've done with ice tables, that's going to mean we're minus x plus x. So here is our ice table. Okay. We then know that the Ka is going to be the concentration of our H3O plus, concentration of our A minus times the concentration of our acid. And we know these values are, actually, let me just go ahead and rewrite it down here since we know the Ka as well. We know the Ka of 1.8 times 10 to the negative fourth is going to equal x times x over 534 minus x. Okay, so there's an assumption that we can make here that if it's correct or valid, then we can avoid using the quadratic. And that assumption is to say, because we are dealing with a weak acid, because we expect a low ionization, percent ionization, we can actually just go ahead and drop this x value off here and just make this value 0.534. So what that does for me is it allows me to solve this out, right? So then I can multiply 0.534 times the 1.8 times 10 to the negative fourth, and I get 9.6 times 10 to the negative fifth equals x squared. Okay, let me go ahead and move up here, which then means that x is going to equal 0.0098. Okay, if the assumption we just made that x, that amount of ionization is going to be very small, less than 100%, we need it to be actually less than 5% to be able to do to make that assumption. So what I need to do then, kind of off to the side here, is just check that and calculate our ionization, our percent ionization. Again, so we have the x, which remember, let me pull it down a little bit. Remember, we called x the concentration of H3O plus. So we have that. If I think about my formula here, we have the concentration of the H3O plus, and we have the initial concentration of our acid, and we do this times by 100, and I see I have 1.8% ionization. Okay, if this is less than 5, okay, so since this is less than 5%, then that assumption that we made and dropping the x out of there is valid. Okay, if this value were to be greater than 5%, then I have to go back in, I have to leave the minus x in there, and I have to set up my, and solve the quadratic equation. But in this case, since it's less than 5%, I'm done. I have solved for x. Okay, so now kind of to finish off what the problem was asking for, it was asking for the concentration of H3O plus, the hydronium ion, which we now know is 0.0098. Molar, and then it was asking for the pH. So if I take the negative log of that, I get 2.0 as my pH. Okay, so a nice little break there. If, again, our ionization is small, less than 5%, then we can avoid having to solve for x using the quadratic. That wraps up this section on acids and bases. Now time for some practice.